Good morning, and thank you for joining our webinar today on radiant section. This is the second part of the radiant section sizing for fire heater design training. This is the fourth webinar in the 12-part series that Furnace Improvements is conducting. My name is Ashutosh Garg. I hope by now all of you know me. I am a chemical engineer and I work as solution provider with Furnace Improvements. And want to thank all my team members who have helped me in drafting this presentation. So they have worked very hard putting all the presentation together. So thanks to all my team members. So we will talk about radiant section sizing today. But before that, I just want to take a couple of minutes to talk about our company. We started Furnace Improvements back in 1996. And currently we have two offices, Sugar Land, Texas, and in Noida, India. Noida is the main office, engineering office now. And our work mostly revolves around improving the performance of existing fire heaters. We also have a different approach. Unlike most of the heater vendors, we work directly with end users and owners. And what we do is we try to provide unique value-added solutions to our clients. We take pride in doing high-quality technical work. Because of the time difference in two offices, we are able to work around the clock. We can maintain tight schedules, and we believe in doing it once, doing it right. That's been our motto for the last 25 years, 26 years. So we want to thank all our clients for giving us business for the past 25 years and keeping us in existence. We have completed 26 years. So all the clients, Phillips 66, Citco, Delec, Valero, Line Oil, they have been our repeat customers for almost 20 years, 25 years. Furnace Improvements is just like any other heater vendor. We have 7 process engineers. We also have in-house CFD modeling unit. And then we have mechanical and structural group, project group, 3D modeling group. We do our own fabrication drawings. And because of that, we are able to work very fast on a number of heater projects. So why are we doing this webinar series? And this has come as a result of our dealing with end users. And when we review existing fired heaters, we find a lot of deficiencies in many of these fired heaters. And we think that if some of these deficiencies could have been taken into account while the heater was being designed or while the heater was being built, you won't face the problems what most of the users face these days, like high tube metal temperatures, short run lengths, coking issues, tube ruptures in some occasions, flame impingement. So these are some of the common problems most of the users have sent us, that how to increase the run length of their heaters. So we decided that it will be better to go into basics and talk to you face to face about what are the critical parameters that go into designing a fired heater. I know most of you will never design a fired heater, but if you are buying a heater, at least you will have an understanding what is the difference between a good heater and a bad heater? The difference is not much, but if you know, you will be able to make the best use of your money. You will be able to get a better fired heater, and it will help you and your plant in getting what you set up to do it. So with that, we will talk about fired heaters, and this is the fourth session today. In the first session, I just want to cover a little background because some of you may not have joined us in the first or second or third session. So I just want to uh, talk about what we covered in our first session. And all these recordings are available on GoToWebinar website. You can always register and view our past videos. So we talked about introduction to fired heaters. We talked about typical procurement procedures, different types of fired heaters. And then we decided, why not we take a sample problem? And the sample problem is a real life problem. This is a project we did for a client in Louisiana about 8 years ago. So this is a real heater design, what we are doing today, or what we are doing over this webinar. And what are the inputs which are needed for fired heaters, like heat duty, what fluid you are heating, the feed properties at the inlet, outlet, how much space you have, where is the site, what are the ambient conditions, what are the environmental considerations, what type of NOx limit do you have, and then you need to have a little understanding of the design parameters you want to talk about, like fuel, what fuel you are firing, how much sulfur content it has, because it does affect the efficiency and corrosion. Then how much excess air, what type of efficiency are you aiming at? If you have any requirement for waste heat recovery, those can also be specified. So the first webinar, we covered the very basics of the fired heaters. And in the second webinar, we covered combustion. Combustion is very central to fired heaters. It's one of the only process equipments where open flames are there when you access the PEEP doors. So we talked about combustion reactions. We talked about excess air requirements. We talked about typical fuel oil and fuel gas compositions. Covered acid dew point. We also talked very briefly about hydrogen fuel firing, and if time permits, we can discuss that again, because there is a very high degree of interest in hydrogen fuel firing. Maybe it will become a fuel of future. And then we talked about factors affecting thermal efficiency, air preheaters, and waste heat recovery, and did some combustion calculations to demonstrate how fuel combustion and fuel efficiency is determined. The good news today is there are tons of programs which are available, and also spreadsheets which you can use for doing these combustion calculations, efficiency calculations. We also have a thermal efficiency calculator as an Apple app, so you can even use that. So let's talk about the problem, what we have been covering in our webinar. This is a hot oil heater, 126 million BTUs, flow rate of 1.8 million pounds per hour. We are heating it from 480 to 600 degrees. And the client wanted a thermal efficiency of 90%. That's a minimum thermal efficiency which the client suggested. So we will be talking more about it. The fuel is not the actual fuel, but for the course, I decided to take some different components like methane, ethane, ethylene, and hydrogen. So I took those fuels and did a new fuel with 4 equal volume percentages, and that's the fuel we are using. Although fuel does not make very big difference in the overall calculations. Generally, most of the time you are firing natural gas or refinery fuel gas, and that may have a lot of methane or maybe a lot of hydrogen. So one of the first things which we need to do in any equipment design is heat balance. And heat balance is needed to establish the energy balance. And here we did the heat balance, and we are heating the fluid from 480, and we have to determine what type of approach between the flue gas and the fluid needs to be decided, or what are we going to keep. So we decided to keep a 200-degree approach, and I covered it in the second session. The reason we did it was because we had to put an SCR unit, selective catalytic reduction unit, and 680 is the perfect temperature for SCR unit. So we kept that approach, and then to get 90% efficiency, we have to bring the flue gas temperature almost close to about 365 or 350. And with the inlet fluid temperature being 480, the only way we can get that type of efficiency is with an air preheater. So we used air preheater and came up with the air preheater sizing, where we were preheating air from 60 degree to 435 degree, came up with an air preheater duty of 11.3, and our thermal efficiency is 90.2. So we are meeting the basics of requirement of the client of 90% efficiency. And then we did these combustion calculations, stoichiometric calculations, how much fuel gas, what is the combustion air, what is the total fuel gas. And flue gas to fuel ratio is about 20 pounds. Air to fuel ratio is about 18.9. So we did this very simple calculations. You can do it from any chemistry book. And then in the third webinar, which was last month, we talked about radiant heat transfer. What are the different arrangements of tubes? There are tubes which are single fired, double fired. And then we had what is the importance of radiant heat flux, vertical cylindrical versus box heaters, tube size, number of passes, firebox geometry, burner layout, and convection layout. So we did all this in our third webinar. And while doing this, we selected 6 passes of 6-inch NPS tube size or 6.625 OD. And our mass velocity, what we calculated is about 14,400 or so. This coil sizing and number of passes is determined by the pressure drop. And then what we do is radiant section calculations are iterative calculations, and everything in chemical engineering is empirical. So what we do is we make some configuration or develop some configuration, and then we check whether it meets our objective or not, whether it meets the heat balance or not. So we came up with a vertical cylindrical radiant section. Here we are giving you 3 options that we could have selected any of the 3 options. We selected the most optimum option, which was 84 tubes and an H by D ratio of 2.2. So that is the configuration of the heater we selected of the radiant section. And this is how the radiant section looks like. Almost like 60 foot tall and 28 foot diameter, 84 tubes, and we put burners on the floor. So that is the configuration we came up with. And then we came up with the burner configuration. How many burners are we going to put? Because when you are selecting the diameter of the vertical cylindrical radiant section, you need to ensure that the burner circle diameter, and you need to ensure the clearance between the burner and the tubes is maintained. So we came up with this 12 burner at 12-foot burner circle diameter installed, and that gave us a clearance of about 7 foot 6 inches between the burner and the tube. So that was a pretty good design. We proceeded with it. Next thing we need to do in the radiant section design is to estimate or do the preliminary sizing of the convection section, because the bottom tubes in the convection section also receive heat from the radiant section. So as a result, we have to develop the preliminary convection section layout. And here you can see we developed this and came up with the convection section design. And what you need to do is to maintain minimum flue gas mass velocity of around 0.3 to 0.4. We did that, and we came up with the convection section design also. So today, what we will be talking about is how do we do the radiant section calculations. I did some of it in the last time, but that was, I think, maybe done very fast. So we are going to go slow and go step by step today so that you can all understand it. We'll talk about cold plane area calculations, refractory area calculations, flame emissivity, mean beam length, overall exchange factor, and radiant heat duty calculations. So this is what we will be doing today. So no matter which heater vendor is doing design of your fired heaters, almost all of the industry uses the same method which was developed in 1939 by Lobo and Evans. And they wrote a paper which is still being used today, even by the leading computer programs. And it is called a well-stirred firebox model. It assumes that the flue gas temperature in the whole radiant section is uniform. We will talk more about that maybe in the later webinars, but this is the basic equation which is used for radiant section heat transfer calculations. It has two components. The first component, it is a radiation component, and that typically accounts for about 85% of the heat transfer taking place in the radiation section. And the second component is the convection component. Because of the movement of the flue gases in the radiant section, about 10 to 15% of the heat is transferred by convection means. So that second component is the convection component. And if you see, the sigma is the Stephen Boltzmann constant, which I think all of you should be very familiar. Tg is the temperature of flue gas leaving the radiant section. So we measure it in degree Rankine. And then Tt is the tube metal temperature, which is again measured in degree Rankine or absolute. And as you all know, the radiation is proportional to the temperature raised to the power 4. So Tg raised to the power 4 minus Tt raised to the power 4, that kind of defines the radiation component. And thanks to Lobo and Evans, they simplified the heater calculations. And they came up with 3 factors, and that's what we will be talking today. They came up with alpha. Alpha is the absorption efficiency factor. And ACP is the cold plane area of the tube bank in feet square. And phi is the overall exchange factor. We will talk a little bit more about it in the uh, later slides. But these three factors are the hallmark of Lobo Evans, that they kind of simplified the radiation section calculations. So this is the equation which is used with some minor modifications by almost all the heater vendors, including us, in all our calculations. So let us talk about well-defined, heat absorbing surface. It is the heat absorbed is by the radiant tubes, and radiant tubes are getting heat by two methods. Radiation heat tube. One is direct radiation from the flames, and second is re-radiation from the refractory going to the backside. And that is one reason the tubes are spaced generally at 2 diameters, because that's been found very optimal. So what Lobo did was, they this tube arrangement, they changed it and replaced it with a surface cold plane area. They said, okay, this tube surface at 2 diameters spacing or 3 diameter spacing, let us replace this with a cold plane area, which is equivalent to the number of tubes into the pitch, So we calculate that. So it's basically the cold plane area. As you can see, our process engineers have worked this, that this is the actual coil, but we replace it with ACP, which is number of tubes into exposed length into center to center spacing. So basically, this becomes like a cold plane area, but it is not going to absorb all the energy radiated to this thing. So that's where the effectiveness factor comes in. So the factor which we are talking about is alpha, which is dependent on the ratio of tube spacing to the diameter. Based on that, they came up with a factor, and that factor is used for calculating alpha. So this chart, I don't know how many of you have seen it, and it is giving multiple these things, but let us focus on the first one. And on this y-axis, we have the absorption efficiency, or alpha, over here from 0 to 1. And here we have ratio of center to center distance by tube diameter. So this is like 1, 2, 3. That generally we stop about 3, And you can see this is a refractory wall, the way he has done it. And this is the radiating flames. And here you are seeing 2 rows. So I want to clarify something. Like in the old heaters, if you see heaters made in 1930s, 1940s, 1950s, you may find 2 rows of tubes, and especially at the arch level, we have seen even in heaters built around 1950s, 1960s, 2 rows of tubes are there. But as per Lobo and Evans, what they found was that the second row of tubes, which is in the back, was absorbing only 10 to 12% of the heat. Almost 88% of the heat is absorbed by the front row of the tubes, and the second row of tubes was absorbing 10 to 12% of the heat. So that is why in the later designs, they removed the second row and just went with 1 row of tubes. So this chart is for 2 rows of tubes, and this chart is for 1 row of tubes, and this chart is for tubes which are not backed by refractory, like double fired tubes. So this is what we will be using for this chart. Now, to those of you who are interested in fired heater design, there is a very nice paper published in Hydrocarbon Processing by R. and Wimpress. I think everybody knows, maybe familiar with Wimpress article. What Wimpress did was he simplified Lobo and Evans calculations. And he even extended it to the convection section and stack. So that paper, if you have that paper, you can design a fired heater all by yourself without using any other external means. So these charts are available there. This is from our design manual, but these charts are available there. So in our case, the tube pitch is 12 and center to center distance is 1.8. So the absorption efficiency is about 0.91. So you can see over here, we get an absorption efficiency of 0.91. So we have at least calculated ACP, and now we are calculating alpha. So one is there, alpha is there, ACP is there. Let us move on to the next parameter. So we know the number of radiant tubes, we know the pitch, we know the length, we calculate the ACP area, absorption efficiency. So we get an effective cold plane area, which is alpha ACP. We get this. Similarly, for the shield section tubes, which is 0.712 and 0.288, if you add it, it becomes like 1. So you can just use 1 for the shield section tubes. And we know how many tubes we have, 6 tubes, 12-inch pitch, 27 foot long. So we calculate the area of those, and that becomes like 212. So the total area what we have for receiving radiant heat is about 4,600 foot square for this heater. And once we do this, we calculate the refractory area, because that's what is re-radiation. So we calculate the how much floor area is there, arch area. We have taken out the convection section opening, so we get the arch area. And then we get the shielded wall area, pi dh. And by this, we are able to calculate the total refractory area, which will be radiating back to the tube. So this is AR. This factor becomes AR. And that's what we use for calculating our exchange factor. So we use this AR, exposed radiant area, and from there we subtract the total effective cold plane area. And when we do that, we get this AR upon the net refractory area, which is 1638 square feet. It looks a little complicated, but if you go one by one, it is very, very simple. It won't take much time for you to do this. You can do this. And then we talk about emissivity. Emissivity is the ratio of energy radiated from a material surface as compared to a black body. So the tubes are not perfect radiation, but they are pretty good. So a zero emissivity is a perfect reflector and 1 is a perfect emitter. Our tubes fall somewhere close to 1, around 0.9 is the emissivity what we use for our designs. And then what we start doing is we want to calculate the flame emissivity. Now, flue gases have number of components: CO2, water vapor, nitrogen, oxygen, and SOx. And what Lobo came up with, that it is only the triatomic molecules which are radiating, like carbon dioxide and water vapor. And that is one reason why it's the same reason why everybody is talking these days about greenhouse gases, because it's the carbon dioxide which radiates heat back to the atmosphere. You know, so CO2 has this property along with water vapors. And these are the two components which are radiating. I mean, when we talk about radiation, the flame radiation, it's basically the two components in the flue gases which are radiating. So this emissivity of the gas, what Lobo found out, was dependent on concentration of CO2 and H2O, which is basically nothing but a partial pressure of CO2 and water vapor, then furnace dimensions, and temperature of radiant gas and the absorbing surface. So the composition and the dimensional effect is generally accounted by a single term, which is known as P is a partial pressure and L is the mean beam length. So furnace dimensions are accounted by mean beam length, and the concentration of CO2 and water vapor is taken care by partial pressure. So we do this, and then we kind of come out that how we do it. What is the mean beam length? And all to simplify it, all I'm saying is the bigger is your radiant section, the bigger will be your mean beam length. Generally, for any H by D ratio of more than 2, the mean beam length as per Lobo is equivalent to diameter. So our H by D is 2.2. So our mean beam length is about 28.2. And 28.2 is a very big mean beam length, so very good heat transfer is going to take place in our fired heater. And the next thing what we do is we calculate the partial pressure. This is the excess air in your flue gases, and here is the partial pressure. So generally, we are looking at 15% excess air or 3% excess O2 as we call it. And if you look at over here, we get a number of about 0.25. So 0.25 atmospheres is the partial pressure. Mean beam length is 28.2. So the product is P into L is 7 atmosphere feet. So this is the number which we use for calculating our exchange factor. So we take this PL and then we calculate the flame emissivity. So this is again Wimpress article. We take the PL and then we calculate the emissivity. And if you see over here, my PL goes from 0 to 5.5. And what we calculated is about 7. So we are somewhere over here, very much over here, almost at the top. I mean, if you want, you can even extrapolate and get a higher gas emissivity, but we calculate a pretty much like almost like 0.61. So we are doing very well on the emissivity part, flame emissivity. We have calculated using a approximate bridge wall temperature of 1550, and we come up with this gas emissivity. And once we have the flame emissivity, then all we do is come with the exchange factor. We have done the tube emissivity, we take the tube metal temperature, and we calculate the overall exchange factor. And exchange factor is little bit complicated, but it is 1 by ET, 1 by CF minus 1, if you are familiar with Kern, even Kern can give you some of these factors, which again are based on Lobo and Evans. So this basically gives you, as a function of gas emissivity, ratio of refractory surface to cold surface, and an angle factor, which is defined by a little bit like the little complicated formula, but it is given in graphical fashion. So if you have the flame emissivity and you have AR upon alpha ACP, using these two numbers, you can calculate the overall exchange factor. So using this fraction of this one, F fraction of all radiation from refractory reaching to cold surface, and calculating the CF, we get an overall exchange factor, which is 0.63. You don't need to do all these calculations. WimPress has it in graphical form, so you can just go to graph, as I see over here, alternate way. You calculate the flame emissivity, you look at the AR upon alpha ACP, and you get the overall exchange factor. So it's pretty simple what they have done. So it's not very difficult. If you have the article, you should be able to get AR upon alpha ACP, and we are looking at about 0.61. So it gets almost pretty close. So whichever way you do it, you will still get almost very close results. And we calculate this QR upon alpha ACP as a number of 32,000. And then we multiply alpha ACP and phi, and we get a radiant heat duty, including shield, as about 91.5 million BTUs. Now, what we need to do is we need to do the heat balance and ensure that the temperature, flue gas temperature we assumed, is it correct or not? Is it able to give 91.5 million BTUs or not? So we need to do that step, and that's where we, this is calculating the radiant heat duty and the shield heat duty. And you can see only about 5% of the total duty is the shield, and rest 95% is in the radiant. And now we do our assumptions like total heat entering into firebox, how much heat we are putting in, how much is the heat lost, how much heat is being absorbed, and how much heat is going into the convection section or exit, whatever is exiting the radiant section. So we do this heat balance. And by doing this heat balance, we are trying to verify whether all these calculations which we have done are correct or not. So in the old times, when the computers were not there, if you get within plus minus 20 degrees F, you would say that your assumptions are correct and you will move on to the convection section and stack. In the age of computers, we can calculate it within 1 degree, our assumption and what we calculate. So we keep on iterating till we get the exact number. So here we are doing the flue gas enthalpy at the radiant section. We get a firing rate, we calculate the heat losses, we add how much air preheater duty we are recovering. So by doing this, we get a flue gas enthalpy of 424 BTU per pound. And this is the flue gas enthalpy chart. This is the flue gas temperature on the x-axis, flue gas enthalpy on the y-axis, and we calculate a BWT of 1547. Assumed BWT is 1548. We calculate average radiant flux of 10,500. Assumed was 10,000. Now, if your client has said, hey, you can't go more than 10,000, and we are calculating 10,500, then we do need to include, or we do need to modify our design, put a little bit more surface and get a balance between the two. So we had to balance this and we had to balance this. So it still needs one more iteration to get the assumed and calculated fluxes and assumed and calculated BWT within 1%. So if we can do that, that means our radiant section design is complete, and we can move on to the convection section. This is a chart I have used from another article, and you don't need to do too many calculations. This is again based on Lobo and Evans, and all you need to do is, with some minor things, you calculate air to fuel ratio, and you calculate your flux, and you get a pretty good number. Now, this is not valid with air preheaters. It will not give you the correct results if you have air preheater, as in our case. But if you have nothing else, if you don't want to spend time, you can just assume this number and it will give you this one, Or if you don't want to do any calculation, assume 60% and you won't be wrong, So 60% of the heat is absorbed in the radiant section, and you can quickly size your radiant section. So here, this is a small heater, 10 million BTUs, and what they have done is radiant flux of 10,000, efficiency, excess air. They did all this, and by calculating these numbers, they are able to calculate the amount of air per pound of fuel, and using that number, you can calculate your heat absorption, 55%. So you know the total heat duty absorbed in the radiant section is 5.5. We assumed 10,000 flux, so we can calculate 550 square of area, and then we can do the number of tubes and size of tubes and number of passes and all those other calculations. So radiant section is not very complicated. As a client, I will tell you a couple of things. What you need to see is, the bigger the radiant section, the better will be your heater. More heat duty in the radiant section means better heater. Lower heat flux means better heater. Other thing which you can see in vertical cylindrical heaters is to calculate the floor heat flux. Floor heat flux is nothing but total heat duty divided by the area of the floor. And lower the number, better your heater will be. Also, H by D is a good indication, If you go for a higher H by D, you will be coming up with a tall and narrow, and that will lead to lot of operating issues. So do not go very high on H by D. So look at the size, look at the H by D, look at the floor heat flux, and these three parameters you will be able to compare different designs and understand what is a better heater for me, as an end user, as a specifier. If I'm buying something, which heater will be better for my client? So these 2 or 3 tips will help you in selecting a better heater. We have a few minutes, so I had received several questions from our participants. So I will take some of these questions. Already we have taken this. So what is the radiant tube spacing? So radiant tube spacing, so in most of the heaters, will be at 2 diameters. What Lobo and Evans did and there are other people also who did the experiments, and they found that 2 diameter spacing is the optimum spacing for most of the heaters. Now, this is very different from the boilers. In the boilers, the tubes are right next to each other, And in fact, they make it what is known as water wall. So there is a big difference between boilers and fired heaters. In boilers, we are generating steam and we are heating water, which is the very good conductor of electricity. Whereas in fired heaters, what we are doing is heating hydrocarbons. And hydrocarbons are prone to cracking. So we have to be very careful and we have to heat them uniformly. And that is why we came up with this concept of 2 diameter pitch, so that we are able to heat the back of the tubes. And the distance between the tube and the refractory is kept about 1.5 diameter. So the tubes are not next to the wall. They are given a space so that the radiation can come back and hit the back of the tubes. And that is generally 1.5 diameter center to center. So 2 diameter is the most common spacing. Now, a lot of times we use 3 diameter spacing, and generally the 3 diameter spacings are used for minimizing the tube metal temperature or minimizing the maximum heat flux. So the reason we do that is by 3 diameters, we are able to spread the heat more uniformly. So for 2 diameters tubes, maximum flux to average flux ratio is about 1.8. And if we go to 3 diameters, we reduce that to 1.5. So if we want to reduce the maximum flux, especially in coker heaters, the last 4 or 5 tubes are spaced at 3 diameters because we want to reduce the maximum flux. So for all heaters, 2 diameters work out, but for some heaters, we can even go to 3 diameters. That is generally the tube spacing. And as I said, we used to have two rows of tubes, and from 2 rows of tubes, we have gone to a single row of tubes now. There has been a lot of interest in hydrogen. So what we did is, this was a question we received from one of the participants. Will hydrogen-rich fuel gas impact the radiant section sizing? And what is the effect of hydrogen-rich fuel gas on the tube skin temperatures? So instead of giving my opinion, I think what I thought was we will do an example. And we came up with the comparison of methane, which is the most common fuel as we use it today, and hydrogen, what we are proposing to use maybe in the next decade. And if you look at the things, methane has a molecular weight of 16, hydrogen has a molecular weight of 2. If you look at the heating value per pound basis, methane has a heating value of 21,000 BTU per pound, and hydrogen has a heating value of very high, 55,000 BTUs per pound. So almost like 2.5 times is the heating value of hydrogen on the pound basis. But then if you look at the density, hydrogen is almost 10 times lighter. The one thing which also differentiates methane and hydrogen is the flame speed. Hydrogen burns almost 12 times, 13 times faster than methane. So one good thing will be the flames will be much shorter because the flame speeds are much higher. So you will get very short flames with hydrogen, which is a good thing. Your air to fuel ratio we require per pound. So you will see how it really won't make much difference when it comes to hydrogen. So my process team has done this simulation of the VC heater, and he has used 2 fuels. One is with 80% methane and 20% hydrogen, another is 20% methane and 80% hydrogen. And if you look at over here, the rate of fuel fired in terms of pounds goes down with high hydrogen. Volumetric fuel firing flow rate goes up. So what it means is the pipes will have to be much larger. The fuel gas pipes and the burner nozzles will have to be changed because now we are passing almost double the fuel, or maybe even higher, When it comes to the total flue gas generation, it is going to be better in terms of total mass. Our flue gas flow rate will go down. So what it means is the draft position will improve. You will not have, the stacks will be sufficient, stacks won't this thing. There is a little bit increase in the radiant heat duty, means more heat duty is absorbed in the radiant section. Little higher flux, radiant film temperature may go up. If you look at the flame temperature is going to be 3300 versus 3500. So there is almost like 200 degree hotter flame, which is not much, I mean, if you preheat air, you get almost same number. NOx emitted is 38 versus 54. I think this is not absolutely correct. With hydrogen fuel, you may, we'll have to see how the burner works and what can be happening. The NOx will become an issue, may become an issue. So I don't see very big difference in hydrogen firing. I mean, there are some refineries who are trying to fire hydrogen maybe in the next few years. So that is, I mean, it should, existing fired heaters will work. Maybe we'll have to change the burners. We will have to change the burner tips. Maybe some control valves in the fuel gas, those type of things will have to be modified actually. Another question we received was average radiant heat flux. Is a heat flux based on just radiant surface area or both radiant and convection surface area? So the radiant heat flux is based on the radiant surface area. So you can say total heat absorbed in the radiation section divided by the heat transfer area provided in the radiant section. And as per API 560, radiant flux is based on single row of tubes spaced at 2 nominal diameters. And generally, we take the first row of shield section in radiant section. And as I said, we did that calculation. We were getting about 5% heat in the radiant, in the shield section. So about most of the heat is still absorbed in the radiant section. 5% is absorbed in the shield section. Now, flux is inversely proportional to heat transfer area. I think that is very clear. Flux is heat absorbed per unit area, And another thing you can think about if you're specifying a heater, the lower flux will get you a better heater. Lower flux will get you a higher heat transfer area, and that's what you will get. And the cost, of course, if you specify lower flux, the heater cost is going to be a little higher, So anyway, you have to kind of think about, are you talking of the initial cost or the operating cost, Heaters with higher radiant flux may lead to shorter run length, and that shorter run length would mean you may have maybe in a 10-year period, instead of having 2 turnarounds or 2 cleaning cycles, you may get for 3 cleaning cycles, Is that extra cleaning cycle going to wipe your entire savings? That's what you have to kind of evaluate. and move on. Another question we got was how to determine the tube side pressure drop in case of vaporization. So pressure drop in two-phase flow is complicated, and there are lots and lots of papers, as well as in Perry, a lot of formulas are there. In heaters, what we do is we simplify it, and all we are doing is we calculate the specific volume. We calculate the specific volume and we use a single equation, delta P by delta L, using that same Fanning friction factor and mass velocity QL plus QV, and we calculate this specific volume, and that's what we use for. So coil failures, I think I would like to do a full webinar on how to reduce coil failures in radiant section. My team has done this slide. I will cover it. So most of the coil failures occur due to hotspots, flame impingement, and high tube metal temperatures. If you want to follow conventional approach, you need to increase the size of your firebox, which may not be possible if you have an existing heater. So furnace improvements has this technology which has been proven in several heaters, and we take your existing burners and reorient them away from the tubes at about 3 to 5 degrees. And by that, we are able to move the hottest flames and flue gases away from the tubes. And what we have found is the tube metal temperature goes down by 100 to 200 degrees in most heaters. You can see this is a CFD model of a heater which we have done. And you can see the flames are in the center, and this is basically hot, cold flue gases, surrounding the tubes. And by doing this, we are able to eliminate flame impingement. We can do this in tight fireboxes. We can use it with low NOx burners or ultra low NOx burners, and we get a reduction of almost 100 to 200 degrees. We have done it in several heaters, and it's been extremely, extremely effective. So if you have a heater where you are having high tube metal temperature issues, give us a call or talk to any one of us, and we'll be able to help you out. You can see over here, this is an existing heater model, CFD model, and where you can see the flames are impinging on the tubes. And here, by reorienting the same burners, we were able to keep the hot flue gases in the center and keep the cold flue gases near the tubes, and we were able to get 200 degrees lower temperature. So I think we are almost out of time now, but if you have any questions, please don't hesitate to contact us. If you have any issues with fired heaters, please tell us or call us. If you are looking for new fired heaters, we can help you get the best fired heater at the lowest price. Well, thank you very much, and thanks for giving us a patient hearing. We'll see you in the next webinar. Thank you. Bye.